I'm going to attempt to review some biostatistics from our community course. This is a quick review to provide a little bit more insight and possibly understanding for the upcoming boards. If you have any questions, please make note and send me an email so I can answer them. Data analysis is the heart of any type of research. It is a process to systemically examine the data that is collected to try and identify any particular information that is of use. Data analysis is the foundation of scientific research, and conducting a complete analysis of the data that you collect will enable you to determine the impact of the work, assess any type of programming that has been developed, and communicate your results to any type of stakeholders involved. I know in the course we reviewed several types of research design, but let's go back to the basics and look at the three broad types of research design ranging from true experimental to non-experimental. The research design chosen for a particular study must align with the purpose of the study and the evaluation and the type of data that's going to be collected. The diagram identifies the most rigorous type of research design, which is more of a cause and effect, and we call that true experimental, all the way to what is the least rigorous, and that is our non-experimental designs. The two types of data collected depend on the research question that's going to be asked for the study. There are two types, qualitative and quantitative. Both types have strengths and limitations and may be appropriate for different settings, evaluation techniques, and evaluation reports. Qualitative data consists of words and narratives. The analysis of qualitative data comes in many forms, including highlighting key words or extracting themes and elaborating on particular concepts. Quantitative data is more numerical in information. The analysis, which involves statistical techniques, and the data is collected by guides that follow analysis processes. One example of qualitative data would be to conduct a focus group with parents participating in an educational program, or to gain information or understanding of the participants. In this case, the data that is collected was probably more narrative in form, and the use of qualitative techniques to analyze the transcripts and looking for particular themes or comments that are made and that seem to be consistent through evaluating the program. An example of quantitative data would be the administering of a statistical survey, asking participants to rate their experiences on a scale of 1 to 5. We refer to that as a Likert scale. In this case, the data would be numerical in form and would use statistical techniques to draw conclusions about participation satisfaction. The two tables below will detail the strengths and limitations of both types of data collection. When using qualitative data, we take a look at the strengths. It gives us a nuance of understanding, more in-depth understanding of the participants or the perception of the participants. We can support or explain the results indicated by the quantitative analysis. Sources for detail of rich information we gain from these types of patterns that we see in behaviors and people introducing particular ideas are the strength behind this qualitative data. The limitations, though, may lend itself to working with a smaller population and may not be representative of the larger demographics. The data analysis can be very time-consuming as the transcripts have to be reviewed and the themes have to be looked for and the particular repetitive words have to be analyzed to see if there is compatibility between the two concepts or the two thoughts that are brought by the participants. Analysis then can be subjective. There is potential for evaluators' bias in the analysis or in the collection, which tends to weaken these type of qualitative studies. When we look at quantitative data, we look at its strengths because they're clear, specific, and numeric. They're accurate and reliable as far as when we do our analysis. They can be easily communicated via charts and graphs, and then also there may be data sets out there that can be utilized in the study that already exist. The limitations, though, to this is that the data collection methods provided respondents to answer a number of response options. They can require some kind of complex sampling procedures. They may not be accurately described as a complex situation, but then it is complexity within this collection of data. This requires some expertise when statistical analysis must be run in the selection of tests and the analysis of the data results. In the last slide, we reviewed a little bit of qualitative and quantitative data. And surveys primarily collect most of the data that we use in biostatistics and any type of health science area. So the rest of this module are going to focus on analyzing quantitative data. Surveys can contain many types of questions, and these questions often are called variables. There are some basic types of variables. It is important to understand the different types of variables because the types of variables can lead to different kinds of data and the study of our analysis and the types of analysis that we will run. There are three main types and categories. We have categorical data, which has binary, practical, and ordinal. We haven't mentioned practical in the previous lecture, but it is introduced now. There are two types of continuous variables, which are interval and ratio. Categorical variables are just as the name implies. They are categories made up of different items. Now, these items are a set number of categories that provide specific information, and they're distinct from one another. They're like providing information on a marital status, the sex, or the ethnicity of someone. A unique characteristic of variable data is that we use binary or nominal codes, and they are provided given numbers, numerical representation of that particular category. As an African American would be 1, an Asian 2, Caucasian 3. We get and assign these numbers are kind of arbitrary. So they cannot be numerically ordered or put in an ordering system whatsoever. They just are categorized and given a numerical representation. There are two types of variables that we list as distinctive, and they're mutually exclusive, what we call, of each other. And that makes them what we call binary variables, such as male or female. When we look again at nominal variables, and we know that they are categorically in design, they must be two categories to select from. So as an example, we look at how would you describe yourself? African American, but not Hispanic, American Indian or Native Alaskan Indian, Asian Pacific Islander, Hispanic, white, or other. Now, another type of categorical variable is our ordinal variables. And these particular variables can be ranked or put in order of how they are aligned. There are no particular criteria or increments between each of the categories. However, they can be placed in a ranking style from low, medium, or high. We know that high is more than medium, but we don't know exactly how much. So they're put into particular categories within the categorical type of data collection. What is the highest level of education completed? Is an example. Less than high school diploma, college, associate bachelor's, so forth. So you get an idea that this particular type of ordinal variable is a ranked type of system. Let's take a look at our second type of variable. We're looking at continuous variables. A continuous variable takes on any score or value with a measurable scale. In addition, the difference between each of the values has some type of meaning. Familiar types of continuous variables are income, temperature, height, weight, distance. There are two main types of continuous variables, interval and ratio. A ratio variable can be placed in order, in which the distances and meaning between each category is equal or static. And let's take an example looking at temperature, 99 degrees, 100, 101. When we look at ratio variables, they are similar to interval variables, but they have one main difference. The ratio of the score makes sense. Let's say if somebody is given a stress level score of 0 to 10, and they say their stress is 10, and another person says their stress is 5. We know that the stress level of 10 is twice as much as the stress level as 5. As with age, height, weight, there's a good example of these ratio variables and how they respond to each other, again, giving meaning and balance between the two. Okay, now that we've reviewed the different types of variables, we need to know how to use these numerical responses, these variables in our studies. So we're going to look at analysis. And the analysis of numerical information produces what we call the results of data. Interpreting data through analysis is key to communicating the results in our studies. The types of analysis depends on the research design, the types of variables we use, and the distribution of data. Now, there are two types of analysis, and we have talked about them before, but let's go over them again: descriptive and inferential. Descriptive analysis tells us about the basic qualities of the data. They describe the analysis to include descriptive statistics, such as the range, the mean, minimum, the maximum frequency. It also includes measures of central tendency, such as the mean, median, and mode, and also, something important, the standard deviation, which tells us what the data looks like. There are many ways to describe data, and we use descriptive analysis to tell us what the data looks like. Below, we will go over some common ways to describe data using a set of scores that we've obtained through tables and examples, how we use descriptive statistics. The first thing we want to mention is that the measures of central tendency. The measures of central tendency is like a snapshot of how the participants look in the study and the results or the data we collected from these participants. So we look at them through measurements of mean, median, and mode. So let's take a look at some common descriptive statistics. When we look at range, we are looking at the difference between the highest score and the lowest score. Minimum being the lowest score in the data set, maximum being the highest score in the data set. And the frequency is the number of times a certain value will constantly appear. Bringing to mind our board information, this type of descriptive statistics or testing does not involve any type of hypothesis testing. It is strictly to describe the sample or the test results. Now we're looking at measures of central tendency. We look at the mean, which is the average of the sum of all the data points that we've collected. When we look at median, we're looking at the score that actually falls in the middle. And if we have an odd number, we're going to average the two out and then divide by 2. The mode is the most frequent data score that occurs within the data set. It's the one we see the most of. So let's take a look at the analysis of quantitative data. We think about how participants respond in general, and then we take their responses and we do our little analysis, and we do a median, and a mode of the data. And we need to consider how far apart or how close these responses are and where they fall in our little bell curve to understand more about the nature of the data and what it looks like, and then how we divide it up between standard deviations. So when we look at a standard deviation, we measure how close the scores are centered to the mean score, the average score. The standard deviations tell us the distance or how far the spread of our data is across from 0% to 100%. So a standard deviation represents the average amount that a score is given to the main mean score in the middle, and then how it deviates or how it spreads away from the center score. A little tip to remind you for boards is that standard deviation is a measure of dispersion or spread of the data. It's the range the data is distributed across the bell curve. Okay, let's take a look at the second type of data analysis, and we're going to look at inferential analysis. Inferential analysis uses statistical tests to see whether the patterns that we can see or that are appearing in our descriptive statistics visuals or images are really are occurring because of chance or because actually the intervention effect did take hold. Research always uses inferential analysis to determine if there is a relationship between an intervention and its outcome, and then how strong this relationship actually is. So the first step in inferential analysis is to answer the question, what does the data really look like? The types of tests you will choose in your statistical analysis will determine on the appearance of this data. That concept may have been missed in our class. So we're looking at how the distribution of data falls. So we look at it in two categories. normal distribution and non-normal. We should always check the distribution of our data to see how we will proceed with the selection of tests. So beginning with inference statistics, the type of distribution we look at when we look at normal is called the bell curve. The graph below is an example of a normal distribution and how it should look. This type of distribution shows that the majority of the data that is clustered around one number or value. Usually it's the data is normal. We choose from statistical tests, and we call these statistical tests parametric tests, and they run off of normally distributed data. A little note for your boards is 65% of the data will fall between +1 and -1 standard deviations from the mean. Now let's take a look at non-normally distributed data. There are several ways that the data can be not normal. It could be caused from a small sample size or unusual set of responses that kind of throws the data off. We talked about skewing in class. The data may not be normally distributed, and therefore we have to select a different type of analytical test. So we call these tests non-parametric. So normally distributed data will always run on parametric tests, and non-normally distributed data will run on non-parametric tests. So if the data is what we call skewed, this type of distribution makes sure that the bell curve is not centered. It can either be positive or negative. If the bar chart shows that the data is negatively skewed, the majority of the scores are going to be on the higher end. If the data shows that the scores are positively skewed, the data set or the bell curve will be more to the lower end. Now, there's something I didn't mention before. It has to do with the possible distribution of this data. We have a new word called kurtosis. This describes when the distribution is either too pointed or too flat in our data collection. So this again can also be, this kurtosis can apply to normally distributed data or non-normal distribution data. Let's move forward and start taking a look at sampling technique. We're going to leave behind the distribution of data, and we will come back to analytics when we start looking at creating or selecting the appropriate statistical test. But right now, let's take a look at how we obtain our sample so we can collect the data. In this little chart, look carefully at the sampling techniques. We have probability and non-probability. When we select non-probability sampling, we have 4 opportunities or most common types of sampling techniques: convenient, judgmental, quota, and snowballing. When we have probability sampling, we have more experimental, more, I would say, stronger sampling techniques. Simple random sampling, systematic, stratified, cluster, and there are some other sampling techniques that they're just not as common. So when we look at the type of sampling technique, it has a reference to how strong our research is. When we go with something that's probability sampling, that means we can predict on this type of sampling because there's a probability tied into it that we're going to be correct. When we do a non-probability sampling technique, it's going to affect the type of test we're going to run, and the data is not going to be as strong. So if we had to determine between the 2 types of sampling techniques, probability is going to give us our most robust and more credible type of results. So keep that in mind as we move forward and work through some of our analytics when we're deciding on what type of tests to run on our sample and in our study. A little note for your boards: when you're looking at the 2 and from least to most, the least amount of bias you're going to find will be in your simple random, which you should know, and the most amount of bias you're going to find in judgment sampling. Looking a little closer at probability sampling, we have to understand that it is a sampling method which all the members of a population have a pre-specific and equal chance to be part of. This technique is based on randomization principles, and within the procedures is so designed that we can guarantee that each and every individual of the population has an equal selection opportunity. This helps to reduce the possibility of bias in selection of our sample. Statistical inferences can be made by researchers using this technique, which makes it so valuable and such a strong way of collecting data. The results obtained can be generalized from possible surveys of sample populations, and the methods of probability sampling are then divided into the 4 methods that we discussed. Now, looking at non-probability sampling, all the individuals of the universe are not equally have the opportunity to be a part of our sample. The method is then called non-probability, and under this technique, as such, there is no probability attached to the unit of population in the selection, and it relies on a subjective amount of judgment. Therefore, it's going to have an effect on the quality of the research or the predictability of the research. So again, there are 4 methods, common methods that we mentioned earlier. And keep in mind that these are theories. Every sample must meet some type of criteria, and we're going to talk about that later, whether or not they are open to the general public or if it's a selected bias. So in separating these two, even though with random sampling or probability sampling, we do want our population to have a criteria to meet our study, we still open that study up for whoever is available or whoever meets the criteria, and it's to anybody that's obtainable, which is not the situation with non-probability sampling. This chart may shed a little bit of light on what we just spoke about, and I'm looking at the chart, and to one side we look at a population which produces parameters, and then we have a sample which opens it up. Within our sample, we drop down, we have probability and non-probability, and how we collect our data from the population or the sample. So we're kind of looking at samples right now, and a non-probability selection sample does not permit the estimate of parameters. The probability produces, probability sampling produces statistics for estimating parameters. So as we look down and we look at the type of selection, and we're looking at non-probability versus probability and how these parameters are established, again, it goes back to the selection criteria or the type of selection we created. If we're doing convenience and quota sampling, we know this does not allow us for parameters. And as far as compared to probability, which gives us parameters, this goes back to when we mentioned non-parameters in our selection of analysis and parameters. So we will come back and visit this when we're selecting the appropriate test to run on our data. In this chart, I want to highlight the comparisons between the two and point out the things that are the most important. Drop down and look at research under basis for comparison. When we look at probability, we look at research category, we look at something that's conclusive, that gives us an answer, which goes back to the experimental design. When we look at non-probability, we're looking at something that's more exploratory. It's going to give answers, but it's not going to answer a question. When we look at the results, we know that with probability sampling, the type of selection is very is non-biased, and that is going to reflect in the results as opposed to non-probability sampling. When we look at the comparison between the two, we know we will, as far as inferencing, in probability sampling, we're going to do statistical analysis, and we are going to run tests, and the numerical outputs have meaning. Where with non-probability sampling, we run analytics. We are going to evaluate. We're going to make a decision about certain things, or make a come to a conclusion about something. We're going to generate ideas, where that's where our hypotheses grow. With a hypothesis under probability sampling, it's tested, and then we have statistical analysis behind it to answer a question. The methods, and it's not mentioned, but the methods for probability sampling are very objective. You have your answers, and they can't be fudged too much. On non-probability, it's not listed, but it's extremely subjective. That means it can be discussed, it can be sort of like torn apart, and it can also have give you questions that may not be answered, and then leave you to understand that the study is not complete or is not totally accurate. So looking at the comparisons between the type of results we get from the type of samplings we do helps us with the type of studies we are going to have each of these sampling groups apply to. Let's walk through this chart. It's going to give us the questions that we need to ask ourselves when we are determining what are the correct statistical tests to select. And in the questions that you're going to have on your boards, you have to look at the study design, probability sampling, non-probability sampling, and see what tests you would select. But we have to know a few things before we decide on test selection or statistical test selection. One, we want to know if we're doing comparisons. Is it just a one sample that we're comparing people within that group? Or do we have two separate sampling options? Do we have group 1 and group 2? So then we're comparing two separate groups. We move down and we look at the data collection points. Do we have 1, 2, 3, or 4? These are timeline things. When we administer an intervention or provide a test, let's say we just have 2. One is a pre-test and a post-test. What if we have 4? Well, we do a pre-test, 2 interim tests, and then a post-test. So those are different times that we're going to collect data on our group. How many observations are we going to have? 25 or less than 25 or more than 25? We know that the number that I mentioned in class was 30. 30 is always a little higher number and you get a better cutoff. So we know that that's going to have an influence on our statistical tests, and we'll mention that later. What about when we go all the way back to the selection of data, or the data we're going to use to run these tests? We know we have two, categorical and continuous. When we have the categorical data, remembering that we're taking binary, which is 0 and 1, or nominal and ordinal data collection, this is a descriptive type of thing. We're going to describe our population or our sample. We're going to describe the participants, and we're going to describe the data we collect. All right, but continuous data gives us intervals and ratios, and that is the data we use for inferencing. So when we look at the data, which we've collected from our sample at different points in our study, and if we're comparing, either we have two different groups of data, people that we used, or one group, we can then determine what the data looks like. We pull it all together, and we run the data, and we do just a descriptive look at the data. And this is when we're just running the basics on it, and we want to know if it's normally distributed or not normally distributed. This has a lot to do with the parametrics of our data, where we have a parameter where everything is nicely bell-curved, or we have non-parametric tests because our data is skewed. We'll go a little bit more into that in selection of data, knowing that what our data looks like that we've collected from our sample. Let's take a look at statistical test examples and how we select the right test for our study, depending on our study design. Let's first look, now remember we're doing some type of experimental research here, and we're reviewing a few things from previous slides. It is a quantitative study. It is, our selection has been probability sampling. So we're eliminating some of the things that are going to interfere with our study results. So we're just basically going to some very specific scientific or experimental design. We have a study 1, which is our pre and post test. This is an 8-week program on home care. We are using one elementary school. We have one group, and it's a home care and a satisfaction type of study. So we give the students a pre-test and a post-test. We find out that our distribution is normal, and the type of variables are ordinal, 1, 2, or 3. We have provided them with more of a Likert type scale, so we have very satisfied, satisfied, and not at all satisfied. The test selection for this will be a paired t-test. Moving on, and now our distribution in the second study comes out non-normally distributed. Our bell curve is off. We then do not select a paired t-test. We're going to select a Wilcoxon sign rank test. Wilcox is what it's called. So you don't have to be specific to know the breakdown of the different Wilcox tests. But so we know that we're just doing a simple pre and post test design on the first two studies. One time our distribution is normal, one it is not. So if it's normal, we're going with a paired t-test. If it's not, we're going with a Wilcox. The second or third study design is a pre-test where we have a pre and post test where we actually have a control group. That means we have two groups now in the study. So, and our distribution has now become non-normal. And again, we're going to pick a Wilcox test. The last study that we're going to look at is a pre and post test. And let me go back to the third test I didn't mention. Look at the number of participants. We are at 25. So we're kind of under that 30. That's going to skew me right there. That tells me I've got some non-parametric tests that I may have to do just by looking at my study participants number. And again, that follows up with the Wilcox test. So the last study is a group of 50 people, nice and strong. We have a normal distributed data collection. We have 2 time points, pre and post test. We're actually just, with this particular test, we are trying to determine between the 50 with the intervention or not the intervention, which may kind of sound like we have a control there. And we're doing plaque score. And again, we have a paired t-test. So these tests kind of are consistent with the type of studies that we are doing and what we will select from. This slide comes directly from your biostats lecture in community. Take a quick look at the difference between parametric and the tests that go with that particular type of test results and non-parametric. Now remember, we determine this by the distribution of the data. Normally distributed data will run parametric tests, and non-normally distributed data will run non-parametric tests. Going back a step further, we want to look at probability sampling and non-probability sampling and how our sample may affect the type of test we're going to run and the distribution we're going to get. So the very first thing we do after we have selected our sample and then we move forward to testing our sample, we run the descriptive analysis to look at the data and see how it is distributed. From that point, when we're doing our inferential statistics and we want to infer our information, we then pick the right test for the way the data looks. So everything kind of falls in order with from the very beginning on the type of randomization we do with our sample to what happens with what our data looks like when we do our first descriptive statistics on it, then to picking our analysis statistics for inferential purposes. So this little chart will select those tests that will stand out the most. So with non-parametric and let's go back to parametric. With parametric tests, depending whether we have a 1 sample or 2 sample, it's either going to be a t-test or paired sample or paired t-test. And with non-normally distributed data, we have our non-parametric tests, whether we have 1 sample or 2 samples. If we have 1 sample, we're running CHAIS. If we have a 2 sample, we're going to do CHAIS or Wilcox, depending on what we have written into the sample. So those are the tests that you really have to kind of have your eye open for test selection. I'm going to show another slide, and I'm going to try and make it as simple as possible. I like to just touch up on reliability versus validity in research. When we look at research studies, they must be reliable and valid. If they are reliable, the methods that produced or created this study can be repeated and consistent. And there are two types of reliability that we look at. Accuracy among the examiners that improved with calibration, we will call inter-examiner. And the accuracy of the exact same person doing the data collection is called intra-examiner. Validity addresses the truth within the study results, and study results must be realistic and conclusive. After doing all this research, how significant is the research? Statistics can tell us if the results in the relationship we observe are real or just due to chance. We associate them with p-values, and that tell us if they are statistically significant. And if someone says the test was statistically significant, they mean that the results are likely due to the randomness of chance, which is what we want. Many, if not most, tests are set to a p-value of 0.05. Based on this level of confidence, this 95% level of confidence that tells us that the results of what we tested and got will fall within this 29%, this study may then be statistically significant without necessarily being meaningful or clinically significant or clinically relevant. Meaningfulness in a study can be measured by something we call effect size, and that is a little bit different than p-value. Effect size is determined by the number of participants we have in the study. Clinically, though, significance or relevance is dependent on its practicality or importance in treatment. So let's take a look at how the size of our population or our sample size has an effect on showing whether or not a study is statistically significant. If it is not statistically significant, but it may be of clinical importance, it could be because the sample size was small and it failed to identify that there was a difference between the two groups, which we may call control or intervention. If it's statistically significant but not clinically important, it may be because the sample size was so big that every trivial little difference between the groups had some statistical significance. It is important to remember, just because a treatment is statistically significant, better than an alternative treatment, does not necessarily mean that these differences are clinically important or meaningful to one's practice. And the last thing I'd like to touch on is common research article structure. I think the class as a whole did very well knowing where to find particular areas of information from a research article. The abstract is typically a paragraph long. It's going to be a summary, and it will include contents, research question, methods, and findings. The introduction provides the background for the research and any existing research that may have been done. The methods are going to outline and detail information on the participants, their recruitment methods, how data was collected, and any statistical analysis that was done. So this is where you'll see what tests were run on the study or on the participants in the data collection. The results are going to provide findings, the statistical analysis, the descriptive stats on the population, and anything of significance. You're going to see as the author describes and details the information as to how they interpreted the results of the study. And in the conclusion or the discussion, you're going to see the key findings, the meaningfulness of the study, sort of like the large picture, and any direction for further research that needs to be done. And also in here, you may find the limitations of the research that had an effect on the study results.